Okay, so here I'm looking at solving the wave equation for a 2D parabolic mirror. I was interested in this because we have a small radio telescope, 2 meters in diameter, that our students use, and we observe at 21 centimeters. So obviously the ratio of wavelength to diameter, lambda on d, is about 0.1, and so this tells us about the resolving power and diffraction from the telescope. And so I actually wanted to see this in action. We know that the Rayleigh diffraction criterion would say that two sources will be resolved if they're separated by an angular distance of around 1.22, is it? Lambda on d. I never remember if it's 1.22 or 1.33. Although the full width at half maximum beam width, as we call it in radio astronomy, that is the full width at half maximum of the central diffraction peak, and the area diffraction is approximately lambda on d, something like 1.03 lambda on d, in radians, of course. So, but I actually wanted to see this more in action. And so I've gone ahead and just solved a scalar wave equation for a plane wave reflecting from a 2D parabolic mirror. And I've done this using the Wolfram language. And the advantage of this is it's very quick to set up. The algorithms are extremely sophisticated, and you can actually dig down inside. You have the option of doing an ND solve, a numerical differential equation solve, in a very automated way, where you just basically plug everything into the function ND solve and it'll solve it. But for a case like this, where I actually it's a fairly memory-intensive computation, you can dig down and break it down into parts and do much more sophisticated things. And the result's quite interesting too, I think, to actually see. I found it very instructive myself. So I thought I'd just run you through what I've done here and show you the results of it. Because it's memory intensive, we don't need to use the Wolfram language in Mathematica with a history length where we're storing each of the previous expressions that have been evaluated, in one, out one, and so forth. So we just set the history length to 0. If I want to save something, I'll actually explicitly assign it to a variable. So then we start setting up. We've got the wave equation operator here. So here we have our scalar wave equation operator. And for the boundary conditions on a region, I'm going to have this large region. I'm just going to use the Neumann boundary condition that the derivative of the scalar field will be 0 on all the boundaries. So whenever we're on the boundary, whenever this is true, we're on the boundary, we'll use the Neumann value for the boundary condition, equivalent to a reflecting boundary. Well, we have a couple of initial conditions as well, as I'll show. I'll come back to those in a minute. What region to actually set up? Well, here's a plot of the region. So I've just set up this big rectangular region, and I've put a parabolic mirror in the front of it that's focused up here. And the actual region that I'm going to view later on will be just an inner part of the region, because I actually didn't want to be seeing reflections and so forth off these boundaries. So I've solved it over a larger region and avoided sort of any of the reflected energy coming into the region that I'm actually going to plot, which is this smaller region here. And so here's where I've set up this implicit region. So either so it's basically not going to be the mirror, not the region in here, but everything inside this boundary here. So we see there are these two boundaries, the boundaries on the edge of the box and the boundary on the mirror, both completely reflecting. Now we actually want to set this up. So initially I was doing this just using ND solve as one function and letting it do it all automatically, but it turned out to be a bit more useful and efficient to break it down into steps. You can go and have a look at this help page in the Wolfram language help, and there's actually much more in-depth instructions for what to do. And actually what I'm doing is I'm working from this, using the ideas in this section here, where we actually break ND solve down into 3 steps. And so the first one is to first of all use process equations. And so process equations, classifies the differential equation system into an initial value problem, a boundary value problem. Basically determines what sort of problem it is, and it also chooses the default integration methods and generates the state data structure that is sort of the representation of the system at time 0. And then we can use ND-solve iterate to advance the numerical solution. Then finally we can do ND-solve processed solutions, which takes the numerical data, that is the series of individual steps, and then fits an interpolating function through them, if that's what you want to do. That last step can take a significant portion of the overall time, so you might just look at things with numerical data first of all, and then finally get some sort of processed equation at the end when you've got the solution that you're after. So here we are. The first thing I do is set up the initial state of the system. So I use ND-solve process equations. So here are the equations. I've got the wave equation, which is just saying that the wave equation operator is equal to 0 everywhere. On the boundary, it's equivalent to the derivative being equal to 0. And then we've got some initial conditions. So the initial conditions we chose were actually this. Here it is. So here's actually the system in its initial state. And I set up what's effectively a standing wave, the superposition of a forward and a backward traveling wave. I could have done that better, but it was a very, very simple way to set this up, and I just let one wave go to the right and disappear, and the other wave come in and hit the window. So I've set up this wave packet like this. And so to do that, that's actually specified here. So here's my wave packet. You see we've got this sort of Gaussian envelope and this cos function, and also the fact that the derivative of the field is 0 with respect to time initially. So there we have it. We've got our region, our initial conditions set up. We set up the first state and we say, all right, the wave equation operator, that's just the wave equation, is equal to the 0 everywhere except on the boundary, whereas the Neumann boundary conditions, we've got the 2 initial condition equations. We're going to be solving with respect to u. We've got, and we're going to let t run forward from 0 to 40. And we're saying that xy is in the region specified by the boundary, by the region with the boundary that we specified above. We're going to use the finite element method, and I give some mesh options, just saying I want the maximum cell measure to be 0.05. That's giving a size of the mesh. The Wolfram Language algorithms will actually work out a mesh that's optimized for the system I've set up, so the mesh will be finer near the curved mirror, not so fine out in the sort of empty regions. And I also have this evaluation monitor, which just plots out current time as a function of as the value t, which initially is 0, and I have that as a dynamic up here. So this would always be showing the current value of current time. And so once I start iterating, I can go back and watch this, and it'll tick over from 0 onwards, and so I can actually evaluate how the system's going. So then I can iterate it forwards in time. And so I do that, and I come up with a solution. And then I've actually done the process solutions step where I've converted it into an interpolating function. I've got the solution. And it took a few hours to run, but very quick to write the software. And then I convert this into a raster plot, basically. So I just sample the region over a fine grid of points, rectangular grid of points. I've dumped it just in case I wanted to bring it back up later on. And I've done an array plot, and here's a list and a mate of this plot. So let's actually go ahead and have a look at the final solution. Noting that I chose up here to iterate this in steps of 0.1, but I could have done it at a finer scale if I wanted to give a smoother animation. And so immediately the first thing we can see, let's pause that, are the two wave packets that were superposed now heading off in opposite directions. So one will go to the right. Remember, the actual true boundary of the system is much further out here, so we're not having to bother about seeing any reflections from the back boundary, or this wave packet here just propagates to the right and disappears. And so we'll see the wave packet coming into the left and then reflecting off our mirror here. So now we see the wave packet interacting with the mirror, and we can see the reflected wave coming up here. And we can see diffraction of these points. It's a very interesting diffraction pattern, and we can actually see that there's a beam width with first maxima and second maxima on either side that we've talked about. It's now passed through the focal point and passing out the other end. So we can watch it run again. The amount of diffraction is, quite interesting to see. So again, we can see this wave coming in here. It's now coming in and passing through the focal point here. And you can see that if I put a screen in here, there would actually be a diffraction pattern on this screen. There would be maxima or minima on the screen. And the wavefront's very curved. That's coming out. It's not a parallel wave that's reflected out, of course. It's interesting to see the amount of diffraction behind here. And of course, if we had ground here, there'd be reflection from the ground as well and further diffraction. And you can clearly sort of see these diffracted waves other side. So I thought this was a very interesting solution, and it's done a very good job at finding a smooth solution.